All right, chemistry. This is the answers video to the day 43 lesson. I'm going to go through and just walk through the pre-assignment questions. You write them down. If you need to listen to it 2 or 3 times, do that. Okay, so what is thermochemistry? What does it study? It studies the heat in and out of a chemical reaction, and we call that heat enthalpy. Why is heat energy important in the chemical reaction? Because it tells us all of the energy transfer that takes place into and out of that reaction through the chemical bonds, either bonds being broken or chemical bonds being formed. It all goes in and comes out in the form of energy, so we know how much energy is in the chemical bonds. What is the definition of enthalpy of formation? The enthalpy of the formation is the amount of heat into or out of a chemical reaction that creates 1 mole of a chemical compound, such as H2O. And it does so from its most basic elements in their most stable form. Okay, so what we can do is we can say the reaction to create water is 2 molecules of hydrogen gas, 1 molecule of oxygen gas. Now that's hydrogen and oxygen in its most stable form as a molecule, O2, H2, and in gas form. And that's going to produce two molecules of water. Now that can either be in liquid or gas form. We'll just say in this case it's gas form. Alright, so that's how you create water. That's a balanced reaction, but it's for 2 moles. The definition of enthalpy of formation, it can only be 1 mole. So we have to cut everything in half. So it becomes H2. And here's where you get the fraction coefficient, 1/2 O2. It's the only place in chemistry where you'll see a fraction as a coefficient. And that's going to give you 1 mole, we should put a 1 mole here, of H2O. Okay, and for gas form, that has a delta H, and I think it's 245, negative 245. It gives off 245 kilojoules for 1 mole of water to be produced, okay? All right, so that's the definition. Go back and listen to that again if you need to write that down. You don't need to write this equation out. I'm just giving you an example. Okay, what does delta H little circle F mean? It means the standard enthalpy of formation. So this would be the standard, if this is at standard conditions, standard state conditions, this would be the standard enthalpy of formation, and you could put a little circle there. So standard conditions, actually standard state conditions, are 1 atmosphere of pressure, just like STP, standard temperature, pressure, and gas laws, but it's not 0 degrees centigrade. It's roughly room temperature, 25 degrees centigrade. And that's not a firm number, but generally you think of it as room temperature conditions. 1 atmosphere, 25 degrees centigrade. Okay? All right. Why do bond energies provide only an approximation of enthalpy of reaction? So if you take a carbon-hydrogen bond, and here's ethylene. It's 2 carbons and it's 4 hydrogens. And these are all going to be, these are carbon-hydrogen bonds. This is a different molecular structure, different electronegativities and so forth, so the electrons get pulled differently, whereas methane, CH4, these are also carbon-hydrogen bonds, but because the molecular structure is different, there's only 1 carbon versus 2, this carbon-hydrogen bond energy is going to be different than this one. Another thing, if you pull away this hydrogen somehow, and it's going to make the other hydrogen carbon bonds a different bond strength, because now you have a different molecular structure over here if you were to take this away. So it's just that different, there's all kinds of carbon-hydrogen bonds in nature, and so they don't all have exactly the same energy. So the number you see on the sheet that we're about to get to in a minute is the average bond energy for a carbon-hydrogen bond. It's not the exact bond energy of any particular carbon-hydrogen bond. Okay, we're going to move on. I'm going to get rid of problem 5. No particular reason. It was supposed to be part of a Hess's Law problem, and I eliminated that. Okay, here we go. I'm having some problems recording. My recording software seems to be wanting to cut out on me, so I might have to do this in pieces, so be prepared for that. Okay, so enthalpy of formation is the enthalpy, standard enthalpy of a reaction, and this is the reaction we're studying right here. I probably put formation, and I might have put the sigma sign there in class. That was a mistake. So it's just the standard enthalpy of this reaction, or any reaction, but in this particular we're using this one, is the summation. That's the summation sign for math. It means you add up something of the number of moles. So the CH4 has 1 mole, the oxygen has 2, the CO2 has 1, and the H2O has 2. Of the standard enthalpies of the products. And these over here are the products on the right side of the arrow, minus the summation of the number of moles of the standard enthalpies of the reactants. And these over here on the left side are the reactants. So products minus reactants. Okay, so what you're going to do is you're going to line these up so that these, the products, are over on the left side of the math equation and the reactants are on the right. So you're going to kind of switch them around. That confuses students sometimes. They make mistakes which side it goes on. Okay, so here we go. We're going to go for the enthalpy of reaction of this reaction. RxN is the abbreviation for reaction. You'll see that a lot from now on. Equals the sum of the number of moles of the product. So the product, first product is CH4, and it is right here. Excuse me. The first product is CO2. My bad. See, I made that mistake. It's CO2. So where is CO2? It's right here. It's negative 393, and you have 1 mole. So I'm going to use square brackets. I'll explain that in a minute. 1 mole, negative 393.5. I'm not going to put kilojoules or any of that. Just clutters up the page. Okay. Then we have 2 H2Os. And here's H2O down here. By the way, this should have been 1/2 H2O like it was on the previous example I gave on the previous page. Okay. And that's negative 285. And we have 2 moles of that. So it's plus, remember it's a summation, 2 and now I'm going to put the square bracket. So the products are inside the square brackets. They're basically just another set of parentheses, but I don't like to use 2 parentheses side by side. It's confusing. So these are the products right here. And now we're going to subtract. And we're going to do the same thing for the reactants. So it's 1 CH4. So here's CH4. So another set of square brackets for the reactants. And it's 1. Okay. And then we're going to add the other reactant, which is 2O2, to oxygen 2. And that's 0. So we're going to just put a 0 there. And close that. Okay, so there's products minus reactants. Okay, so now what you do is you go ahead and you add these things up. So I'm going to do that. Okay, so I'm back. I'm counting on you to know the basic math. So it's negative 393 times 2. So it's plus 2 times negative 285.8. And that's going to give you negative 571.6, I think. I don't know. Anyway, it's a negative number there and a negative number there. So it's negative minus this number. Plus a negative, or negative minus this number. It gets you that. So I'm trusting that you have the math skills to know how to get from here to here. If you don't, come in and sit down with me and I'll do it with you. Over on this side, you have the negative 74.8. The 2 times 0 goes away. So you have a negative sign out in front and a negative sign inside. A negative becomes a positive. So that becomes a plus sign. If you then take this and add this, you get negative 890.3 kilojoules for this reaction. So that's the answer. It's negative 890.3 kilojoules will come out of this reaction. Now, since this is for 1 mole, it just happens this reaction is for 1 mole of CH4. Not all combustion reactions are for 1 mole, but this one is. Then this is also would be the molar enthalpy, standard enthalpy of reaction. It's the enthalpy heat change for 1 mole, the combustion of 1 mole, 6.022 times 10 to the 23rd of these molecules. It's the heat that comes out of the combustion of 1 mole of CH4. Again, not all reactions are for 1 mole. It just happens this one is. So you could call this the molar enthalpy of reaction for methane. And if you look this up on the internet, molar enthalpy of reaction for methane, you'll come up with this number. Okay? All right. That's the only one really we're going to do on this one. So be sure you understand it. I would practice it on line paper. Again, just watching me do it doesn't mean you know it. You've got to practice it on line paper. Okay? Here we go. Now we're going to go to bond energies. Okay, so these are the average bond energies of various types of very common bonds. By the way, you have the enthalpies of formation and these bond energies in your packet on pages 11 and 12. Generally, though, if I give you an assignment, I will give you something like this. I will give this to you on the assignment. All right, so now we're going to go and do some bond energy problems. Okay. All right. So this is the one I did in class. I'm going to leave you with this one to do. Tell you what, I'll do two of them. I'll do the one first we did in class, okay? In case that you didn't quite understand. So you don't at this time know how to diagram these molecules. Why does carbon dioxide have a double bond there? Why does oxygen have a double bond there? Whereas water has single bonds. You're going to learn that within the next week or so. Okay, so here's what you do. Very simple. Simply, it's a lot of numbers, but it's not that hard when you understand the concept. So we have two molecules of C2H6, and this is the diagram of a C2H6. So first of all, we want to look at the carbon-carbon bond. There are two molecules, so the first number I'm going to write is the number of molecules. That is this number right here. And let me ask you, the first thing I want to write is what am I doing? Which bond am I doing? I'm doing carbon-carbon single bond. Okay, so I have two molecules times there's one carbon-carbon single bond. There's two carbons, but there's only one bond between them. So that's one carbon-carbon single bond. So it's times 1. Okay, and then I'm going to come over to this sheet. And here's carbon-carbon, and it's 347. So I'm going to put that in here. Okay. Now I'm going to come down to the carbon-hydrogen here. Carbon-hydrogen bonds. Again, there's two molecules based on this number right here, and there's 1, 2, 3, 4, 5, 6 carbon-hydrogen single bonds. So it's 2 times 6, and now we come over here to find carbon-hydrogen. It's right there, and it's 414 kilojoules per mole. Okay, and I'm going to go ahead and do the other one on the reactant side here. Oxygen, there's 7 oxygen molecules, and each one has a double bond. There's one double bond between the oxygen, so that's times 1. Now we come over here and find oxygen, and it's right there. Oxygen double bond is 498.7. Okay, and that takes care of everything over here on the reactant side, on this side of the arrow. Okay, so I'm going to go ahead and do the math on that. Let's go ahead and do that. Okay, then when I multiply 2 times 347 and add that to 2 times 6, which is 12 times 414, I get 5,662. For this one, it's 7 times 1, 7 times 498.7, and you get 3990. So when we add those two numbers together, we get 9,152.9 kilojoules. That's how much energy in. That's an endothermic process. Why? Because in order to break the bonds of the reactants, you have to smash them. You have to put energy into them and knock them out, knock them apart from each other. That's endothermic. That's energy in. Now we're going to go over here and figure out the energy for the products, what's going to come out of this reaction. Okay, so here we have 4 molecules of CO2, and each one has 2 carbon-oxygen double bonds. There's a carbon-oxygen double bond. There's a carbon-oxygen double bond. So it's times 2. And now we come and look at the energy for a carbon-oxygen double bond, and you see 2 of them. There's 2 numbers for it. So which one do you use? Well, if you look at this asterisk and read down here, it says the bond energy from CO. It's hard to even see the 2 there. It's from CO2. Okay? So that's the one you're going to use because we are dealing with CO2. There's all kinds of other carbon-oxygen double bonds in nature, but this one specifically for CO2 is very common, and so it has a different bond energy, so it's 799. Okay, now we're going to come over here to the water. We have 6 molecules, and each one has 2 hydrogen-oxygen single bonds. Again, remember what these lines mean. I should have mentioned it earlier. These represent 2 electrons. This represents 2 electrons. So in other words, these 2 lines are a double bond. This is a double bond. So these 4 dots here, which are each electrons, are the same as these 2 lines right there. Okay, just 2 different ways of representing the same thing. Okay, so anyway, we have 2 of these per molecule, hydrogen, oxygen, single bonds, and we come over here, and it doesn't matter if we call it HO or OH, its HO is 460. Okay, so now we have to sum all of this up, so I'm going to go ahead and do that. Okay, so I multiply 6 times 2 times 460, and I get 5,520. Now when I add these 2 numbers together, I get 11,912 kilojoules. Now that's the energy coming out. Why is it coming out? It's exothermic. Because when chemical bonds are formed, in almost all cases, but not all cases, and we'll find out why it's not all cases, they want to release energy. They want to go to a lower energy state, a state where they're more comfortable. That's why they form chemical bonds, because it's more favorable to them energetically to do that. And so therefore, if they go to lower energy, that energy comes out, and that's an exothermic reaction. So this is energy in to break the bonds. This is energy that comes out when the bonds are reformed into the products. So now if we add those 2 numbers, 9152.9 minus, because it's energy coming out, it's exothermic, 11,912. And let's go ahead and do that, 9152.9 minus 11,912, and that gives us negative 2,759.1 kilojoules from this reaction is coming out. Okay, and that's the answer to the question. But most of the time you want to figure out the molar enthalpy of reaction. What would it cost? This is what it takes, how much energy comes out when you combust. This is a combustion reaction, 2 moles of ethane. This is ethane. But if you want the molar, you'd have to divide this by 2. You want to know how much energy comes out for 1 mole of ethane. That's just a standard number that you can actually look up. So if you want that, you take this number, 2759.1, and you divide it by 2, and you're going to get negative 1379.6 kilojoules. So that's the molar. This is the molar enthalpy of reaction. Standard enthalpy of reaction. It's the amount for 1 mole. Okay, now if you look it up on the internet, we did this in class, you'll find out that number is actually negative 1500. That's not very close to negative 1500. And the reason, that's what we said, that bond energies are not a real accurate way. They just give you kind of an approximation. Sometimes scientists don't need to know an exact number. They just need to know, I mean, is it closer to 1,000 or is it closer to 100,000? So here it's close, you know, it's kind of in the ballpark, what they call it, in the ballpark, just close to it. Okay, so that's how you do that. All right, let's do one more. Okay, so I'm going to do this one quietly and real fast, and you kind of follow it, okay? So here we go. So we got 2 carbon-carbon bonds, okay? So you got 3 carbons, but there's 2 bonds between the carbons. So carbon bond right there, carbon-carbon bond right there, okay? So, and this is a balanced reaction, so this has a coefficient of 1. So you have 1 molecule times 2 bonds right there, 1, 2 bonds. And we said before that a carbon-carbon bond is 347. Okay, now we do all the calculations. Okay, so here we go. Now again, if you have trouble with the math, come in. I'll work with you on the math, okay? You don't want to know chemistry and not stumble on this math. So it's 2 times 347 plus 8 times 414 gives you this. 5 times 498.7 gives you this. You add that up, you get this is how much energy you put in to break these bonds. That's an endothermic process. Energy's going in on the reactant side. On the product side, energy is going to be coming out because you're putting these bonds together. They're at a lower energy state. That's why they wanted to get together, so they could be at lower energy. So you have 3. You have 2 per molecule, double bonds of carbon oxygen. And there's the 2. And then 799 is the number that we did. Okay, and then it's 4, and then you have 2 hydrogen-oxygen bonds right there, and the number we got for that was 460. So you multiply these to get this and this, you add them together and you get this. You put the negative sign in front because it is exothermic. Energy is going to come out. Okay, so now when you take the energy in and add it to the energy out's negative, you get a negative number, negative 1974.5, okay? All combustion reactions are exothermic. Most reactions are. That's kilojoules. That's also the molar enthalpy of reaction. Why? Because we have exactly 1 mole here, right there. If we had 2 moles or 3 moles, we'd have to divide by that coefficient to get the molar. But this is already 1 mole, so that's the molar enthalpy of reaction. Okay, I'm going to do a couple of the stoichiometry. I'm going to do one. I want you to do the other. So I'm actually going to look at 4B. Okay, so how much heat is released when 4.5 grams of methane is burned in a constant pressure system? That's not really relevant. The enthalpy of reaction, well, it's telling you that it's enthalpy. That is kind of relevant, but we assume it's constant pressure all the time. The enthalpy of reaction for 1 mole of methane, molar enthalpy of reaction, is negative 890. We've seen that number before, okay? So here you've got grams. You need to convert to moles. So this is kilojoules, and I should have put, to be more accurate, kilojoules per mole, negative 890 kilojoules per mole, okay? So they want to know how much heat in kilojoules. Okay, so how much heat, and that's going to be in kilojoules. That's the measure of heat. So way over here, we're going to put kilojoules. And it's just kilojoules. It's not asking per mole here. It just wants to know how much total heat are you going to get. So there it is. There that is. Okay. We're going to start over here with negative 890 kilojoules per mole. And that should have been per mole, and so should this one down here. So we start way over here. Okay, so let's look at our stoichiometry. We need to get from kilojoules to kilojoules, so we don't need to do anything to the top. We need to get from moles, and it's moles of CH4, methane. And we need to get to nothing down here. We don't have anything on the bottom. So we don't have to do anything on the top. We've got to get rid of the moles of CH4. Okay, so first we need the molar mass. Anytime we're going grams to moles to grams, 1 mole. Okay, and remember we have this gram here, 4.5, to work with to cancel our grams. Okay, so we need to get rid of moles, okay, because it's not on the bottom there. So which one goes on top, which one goes on bottom? I think most of you are kind of getting comfortable with this, I hope. If you're not, you need to just come in and work with me. Okay, so moles of CH4, moles of CH4. Now I have grams of CH4 in the bottom. It has to go away because I don't have any units down there. Well, here we go. We got 4.5 grams of CH4 there on the top. Again, this is all just a puzzle to get units to line up. That's all this stoichiometry stuff is. So grams of CH4, grams of CH4. So we have negative 890 times 4.5 divided by 16.05, and that gives us negative 249.5, and I'll leave it at that. So that's how many kilojoules you would get out of 4.5 grams of methane. Okay? The one down here is exactly the same. I just changed the number of the grams. So do it the same way, just practice it on your own, okay? And that takes care of this answers video for day 43.